Gotta relax.
This is Earth Radio. And now here's human music.
Human music. I like it. I like it. I like it.
Oh, I was coughing. Ha ha ha. Yeah, good run. Depression. Sure. Thank you. Yeah, I was coughing up a lung and figured nobody else wanted to hear that. Fun part was after class the other day, I finished up that run and I died horribly. Steamrolling. Woo! Oh, easy. GG. Go get him, Harbinger. Oof. Hey, back to that win streak of 1. Alright. Hey, we got 10 minutes. It's chaos. So if you've never played this game, this is one of the most annoying characters to play. Absolutely.
Earth Radio.
Love the egg.
And now here's human music.
Basically, this character, if you get... Oh shit, I'm dead. Unless one of these is a teleport.
Human music.
Basically, you can't get
I
hit
like
with
it.
this character, thank God. Okay. Ooh, the moon. But, because I've unlocked the, I don't know what that's called. Cross there, I get one grace period of a hit. Alright. We want that card. For when bad things happen. It's fun. It's just the gameplay is so polished that it's like so good.
I like it.
I keep waiting for a game to scratch the itch that this one does. Haven't really found anything. Gungeon came close, but I did that one and just no desire to revisit it. I did. I have reached it. Is it up here? I did reach the Sunken City, and I think I died on the second part of that, the second level there. Haven't reached it since. The problem is I get overconfident. Nice thing about Spelunky is that it feels like everything that happens is your fault. I like that in a game. But it takes so long to get there. That's kind of the downside. Like, it's a 40 to 50 minute run if you get that far. And you're, not good like me. It is brutal. The first one I could get through to hell and maybe... I don't even remember now, but it felt a lot quicker. And when I'm not on stream, I can pretty much generally beat Olmec without issue. And then I get to Neo Babylon, and that's my current kryptonite is that one. The other nice thing about Isaac is you can save and close it and, do things like teach and then come back to it later. Virgo,
Gotta
pretty
relax.
much useless here.
This
Alright, this is going to be a slow run. Absolutely. Oh god, I had a great pinball. I had a jetpack and Quilin. I got the unlock. Is this gonna double my protection? That'd be helpful. So I popped was that the Ushabti? I don't think I've ever said that out loud, but I was on him, I got hit by a ball, and then my jetpack exploded and sent me all the way down the map. And then the shopkeeper hit me with his shotgun. It's delightful. Yeah. 5 minutes. How's everybody doing today? Class is going all right? The jetpack, yeah, I've got a hard time dropping that. It's so useful. Here's some lectures. Nice. Ah. How are those working for you? I guess, like, so I've got a bunch of pre-recorded lectures I'm making for my grad level cloud class, and it's the struggle of making it interesting, making it useful. Is anybody even going to care about it? Really just like pre-recorded. Yeah. I could see that, honestly. Come back here, please. Alright. Money, money! Yeah. Get some spiders out of this, not bad. Yeah, you're gonna explode.
Gotta relax.
This is Earth Radio.
That's good to hear.
Now here's
I'll have to pass that along to him. I'm sure he'll appreciate that, I'm sure.
Music. I like it.
Yeah. Oh no, 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 no. Didn't want that to happen. There. Shit. I don't get how Twitch streamers do this. I'm looking at chats. Watching that. Ooh, freeze. Sigh. You think you got it. There goes my streak. Oh, it's alright. My only streak I've ever gotten to using the Lost is 2. So, it's not like I've lost much. No you. Three minutes. Alright. This is not the good one, is it? No. Yes. Mantle is... I would not be subjecting myself to this without the mantle. Also, thank you for reminding me what the name actually is. Alright. No idea where we are. Let's go this way. I guess while we got a second here, how'd everybody do with the homework? I noticed pretty much everybody got it turned in. And if you're one of the only ones who didn't turn it in, please feel free to get it in and you can still get points for it. Easy peasy. Good, good, good. It wasn't meant to be hard. It was meant to really get you up and running, so.
This is Earth Radio. And now here's human music.
Next one will be a little bit more interesting. I'll get to that to you all very shortly.
Human music. I like it.
Moving files. What was your issue? I'm kind of curious. Permission restriction. Yeah, so remember var www.html is admin locked? Ah, that happens. Forget they like to stick to you. All right, good enough. Get my streak back later. But yeah, that's a an expected thing.
I like it.
You should be able to sudo around that, basically. I don't know if you all appreciate this, but I was... get out of our human music here. I was working on a demo for the cloud class, and it was a whole bunch of like Kubernetes and Docker stuff. And it was basically working through a lab manual. And the thing with doing labs in the cloud is that file name dot, yeah. You don't need the dot dot slash dot dot there though. So it's just the first slash takes you to the root of the file system. Yep. That's how Linux works. The first slash is the root. Yeah, I haven't graded it yet, so doesn't look any different to me. Wink. But yeah, if I, let's see, so if I have, let's say, touch new file .html, touch new file .js, HS is good enough. So if I've got these two files here and I want to move everything called new file, let's make this bigger so it's wider. Sudo mv new file asterisk var www.html. I was probably going to grade them this weekend, so. But yeah, that's all you'd have to do, and then you see them in, let me bring this up a little bit. That's not helpful. Clear. ls var ww. So just to give you a hint as to why this is the case, yeah, Apache, which is the web server we're using, has some very interesting perspectives on permissions, mainly because they don't want people just willy-nilly editing files on a production server. So basically, you either need to have admin rights, which is sudo, to do anything in there because it's all locked, or you have to join it's the www grep www. Is it? Oh, it's this group. That's right. www-data. Yep, got to join the WWE. And the RKO was WWE, right? RKO out of nowhere. Basically, if you join this www data group, then you can also, in theory, have access to it. I've seen if you look up permissions for Apache, there are so many different ways to handle it, and then you will have an equal number of people telling you that's wrong because it violates security principles. You can take ownership of them. You can create a new group and give that access. Make it this particular permission read and write, but no exits. Just do sudo for now. It's going to make your less of a headache for that. Exist. That's how we spell exit. Yeah. What was I saying? So this Docker thing I was doing, I got through the whole thing, and then at the very end it said, oh, and by the way, to clean up your project, or to clean up all the work you did so you don't keep getting charged for it, delete the entire project. And the first time I did that, I did it in my account that I'm using with you all. And I ended up having to delete my virtual machine because I didn't want to clean up 30 million Docker instances, Kubernetes clusters, and it was messy. All right, you go over here. Okay, so homework was good. That's good to hear. To give you a preview of what you're getting into next time, which, let me pull it up and make sure I tell you the right thing here. It's been a while since I looked at this. Okay, good. Yeah, so our next lab is going to be mainly focused on interacting and animating, which is the next set of slides. So we're going to get through this stuff today. Might touch on interaction and animation too. What we're going to do next week is we'll do an in-class lab to get you all up and running with interaction and animation, rather than just having homework, so we'll do that. But it'll be less basic triangle and more stuff happening on the screen. So with that, I did want to ask, because even though this is not strictly a democracy, I do like your opinions. Am I not covering anything? Okay. So if we were to do an in-class lab on Tuesday, would you rather it be on Zoom or Twitch? Again, I will hold the final decision here just because I'm the one running the class, but if we were to do it on Zoom, I would give you all a handout, we'd work through it, you ask me questions as you go, which is fine. If we did it on Twitch, we'd have the same setup as usual, except I would run through the lab on stream, and you would ideally, in theory, I'll do it at the same time, and you just feed me questions that way. Zoom, zoom, zoom. Okay. It's good for. So basically, I was kind of leaning towards Zoom just to do something different, but the last time I did this poll, there was a lot of strong opinions that people seem to like Twitch better, so I wanted to see if that held here. Again, the goal here is to get you all the information you need from me, right? I want you all to be successful, so whatever's going to work best for you all is okay. All right, so tentatively we'll say Zoom. So that's 9 people so far, and we, I think, have like 15 for Tuesday. Okay. Taking notes in Vim on the side here. All right, I'd say that's enough of a critical mass there. Let's say Zoom on Tuesday. I'll put an announcement out on Blackboard for that. That's kind of what I was leaning towards anyway, so. Yeah, there is that delay. That's the one downside there. Agreed. But it gives you time to, yeah, the delay's a little rough, I agree. But I mean, again, if you have questions and you just want to voice them, feel free to bug me in the Discord chat. Okie dokie. So last time we ended with polygon testing. All right, so we're talking about the issues we have with polygons, with triangles. And let's see, get some extra light in here so I'm hopefully not, camera's doing weird things with lighting. So if you remember, I kind of talked about how we can start drawing things that are not basic triangles or squares. And one of the issues is that WebGL cut out some of the stuff that OpenGL gives you. There is no tessellator built into it. I can't say draw this polygon and turn it into triangles. You have to implement your own algorithms for that. They're not that bad. There are a lot of well-known algorithms out there for this. It would be basically your job to implement it in your particular applications, if that's something that you were going to be doing now. And I showed you this example too, right? So this was Delaunay triangulation. It's Delauney, if you're looking that up. But basically, it's one of the quick algorithms for doing that. Very, very useful. Nice little JavaScript demo here. We will get to that much later in the semester, basically. Okay. So with our notion of polygons, and we talked about convexity last time too, right? Our triangle, or our shapes need to be convex, meaning that there's no like indentations in them. You can't draw a line through it and have it pass through both parts of the object and empty space, right? This would be like a convex image here that you would see. There's no like valleys inside of it. That's what we're looking for in terms of triangulation algorithms and in terms of drawing polygons. And if we have those shapes, we have to figure out how to deal with them, right? So that's going to be one of the other concerns that we have with triangles. Now, the interesting thing with WebGL and graphics in general is that there is a tendency to prefer more of an equilateral triangle shape. So most of the triangles that you're going to see when we, algorithmically create them is that they all tend to be equilateral-ish, right? It's not perfect. We have to make some allowances at times. But the reason for this is that when we have triangles that kind of look like this, so long and thin ones, they don't render out very nicely. You get a little bit of artifacts happening with the shapes. And obviously with graphics power and our graphics cards and our displays getting better and better over time, this issue does tend to get a little bit more minimized. But kind of the key takeaway is to try and avoid triangles like this because there can be this problem. Maybe it's older hardware though, newer ones, not nearly as bad, but still we should try to avoid this. So what does that mean for you all? Maximize the minimum angle of your triangles. And that's the angle, say, in between. Let me get my pointer here to really drive this home. So if you have these little angles that you probably remember from your trig days many, many moons ago, try and make the smallest angle as big as possible. Don't have like a little 13-degree angle. Try and make it bigger if you can. And this will depend on the algorithm used as well, too, right? So for this class, I'm not expecting you to come up with triangularization algorithms. That's like PhD thesis type of work, but be able to at least use them is where we'd be looking at. All right, pointer, go away. So talked about triangularization. Now, what does that mean and what does that mean to you? In terms of actually figuring this out, and again, algorithms for this we'll talk about a little bit later, we need to basically do effectively, it can be a recursive algorithm where you go vertex to vertex to vertex. Your camera is super blurry, by the way. I'm seeing that. Do I have to stand still for a minute? Let's see. Wow, that's awful. I mean, let's be honest. Nobody wants to see me in HD anyway. Come on. It does this from time to time. Let me do this. Or let me do this. Maybe this will work. Could be just that I haven't really shaved in a while. And now it's stuck. Cool. All right. Camera, come back. Camera, come back. Technical difficulties. Please come back. It's not coming back. All right, what if we... Really? Sorry about this, guys. My camera is just blinking blue now. This is hilarious. All right, maybe if we use the onboard camera. Let's try that. Anyway, are we all loving this frozen view of me here? Come on, where are you at? Hey, look at that. Perfect. I'm gonna have to go get a different camera. Cool. Neat. All right, well, you can go away. There we go. Beautiful. Be like elderly chat here. Let me put the camera so that my top of my head's cut off and we'll be good. Oh, this is going to be fun because now I'm going to look over here and be talking to the wrong side. Yay! Anyway, so here we have a polygon shape, right? Okay, I can do this. I've got my preview here I can look at. Oh, this isn't getting edited down. All right, so we have a list of vertices here, right? We have this kind of shell-like shape that we have to deal with. To turn this into a list of triangles, it looks very, very clear what we have to do, right, visually. But what you have to do is think of this in terms of an algorithm, right? So we have a list of these vertices, right? A, B, C, D, E, F, G here. What we might have to do is let's create one triangle ABC. And then in our algorithm, and again, this is not strictly triangle drawing, it's figuring out which shapes we need. Clearly this is a fan. Let's get rid of vertex B. Okay, now we have to deal with ACD, then ADE, then AEF, right? So basically in a simplified view here, and let me get rid of that so I'm not completely washed out, you basically are going to have to figure out which vertices are going to participate in which triangle shape. Right here we would have a triangle fan. If we had something a little bit, more flat, maybe we're not trying to really define like a curve, we might have a triangle strip, or maybe a triangle, or we might have a bunch of points. Effectively, what's going to happen is that we have to have an algorithm or set of algorithms for figuring out how to turn a list of vertices into triangles, and we'll get to that. Okay, so everything we've seen so far has really been convex, right? So here we have a non-convex shape. So we have a list of vertices, right? So we'll call them vi, vi minus 1, vi plus 1. This might be vi minus 2, vi plus 2, whatever we're going to list them as. How do you think, I mean, visually, I'm sure you can figure out how to draw this as triangles, right? But what would you do algorithmically? Like, how could you handle this type of shape? And while I'm waiting for an answer, let's start drawing this thing because we're going to do a little bit of work here with it. So how would you, I guess, figure out, again, algorithmically, what to do with this thing? I mean, this is your fault. Honestly, it's my fault. I pulled the USB cable out, and that just Streamlabs doesn't like it when you do that. All right, so how do we figure out how to turn this shape into triangles? Is kind of the question here. First example up to vi minus 2. Right. So one of the things that we'd have to deal with here is, again, there's going to be multiple algorithms for handling this. I'm looking at the wrong camera. It took me 5 minutes. We have to figure out if this is a convex or a concave shape, or parts of it would be concave or convex, right? So if we are starting here at vi, and I'm trying to figure out how to turn this into triangles, well, let's say that this is my first thing that we're dealing with here, right? So vi, vi minus 1, vi plus 1. We already have a problem because we have this little bit that's cut out here. So if I try to draw just a straight up triangle, it's not going to work. There's this space here. So one thing that we can do is we can have a little bit of a recursive algorithm going on, and we can test for convexity, test for concavity. If we have that test fail, basically meaning that we have a concave shape, we start splitting things up, right? So instead of one polygon, right? We have 2 polygons. So now we have kind of this, it's still slightly concave if we look at it this way, right? But we basically have a rhombus-y type of thing and a paper football type of thing here, right? But if we do that, and let me, let's see, can I get, no, I'm not going to be able to get that. Let's not do that. Let's draw a new line, not in red, thank you, in black. The next one's going to be red. This one's going to be red. Okay, I give up paint. You're killing me here. Anyway, so now we have 2 shapes here, right? So we have this one and this one. Now what we can do is we can basically have pencil. We have vertex here, vertex here, vertex here, vertex here, vertex here, vertex here, right? And then we can start applying our algorithms. So if we have a new list of vertices, we could say, draw one here, draw one here, and then in theory, we're good, right? We have triangulated. And algorithmically, we could figure this out. Doing this again. Camera, go away. Bad, go away. How do you get from here to here to here? Well, clearly we don't have any concavity. If we did this, we could draw triangles, draw lines. And again, we are just pushing vertices to our draw erase function in this case. So that's the kind of thing that we would do here. So we have to have a test for concavity, and then we have to figure out how we're going to split up our polygon. And some of our algorithms will help us with that. And yeah, okay. So we have triangularization, tessellation, also known as. We also can define attributes for our shapes as well. So again, we're still talking about shaders here in an intro kind of high level. These are the things that are going to really show you kind of the appearance of what your shapes are going to look like. And the takeaway is that WebGL does not support all of the things that you would expect it to support, which is mildly annoying if you're coming from a more feature-rich environment. So obviously we get the color, right? So what color are your shapes? We've done that with glfrag color. You should be quite familiar with that. We can define the width of our lines, basically, if we need to. Is it going to be stippled, which is basically kind of like the pointillism. You're filling in a shaded area with like points. There's like no lines, it's just dots making the shape up. And then is it filled? Do you show the edges? Do you show the vertices? And the interesting thing is that WebGL really only supports a very small amount of these attributes. So if you're coming from OpenGL or DirectX, not everything that you're aware of is going to be supported by us, and that will hopefully become apparent as we go. So more GLSL now. We're going to talk about how we compile and link, and the spoiler is going to be that the the libraries we're using make this really, really easy. The stuff that we're going to be looking at here is if you had to do it by hand, which I do not recommend. Use a library, use our libraries from the book author. Don't do it unless you have to. Right. So these shaders that we have, again, they are C-like code. They need to be parsed or read. They need to be compiled. They need to be turned into a program object, which is that like vargl equals, stuff that we're doing in our code. Everything has to be linked. Variables have to be linked. Everything basically has to be set up. And again, this is stuff that you have all seen by playing with these applications that we're, creating from pre-existing code. But this is what's happening. The key takeaway is that your shaders are being compiled. They're not being translated. They're not being interpreted. It is a literal compilation process for the GPU. So this program object that I'm mentioning here, what is that? That is the wrong window, thank you. This is that program equals gl.create program. That is a container for our shaders. We are going to then attach compiled shaders to this program object. And what's happening behind the scenes with our libraries is this attach shader link program call. We don't have to worry about that's happening under the hood. But again, if you're doing this by hand, you would have to actually go ahead and do this stuff. Not recommended. It's boilerplate code that you can abstract away to a library. Even some of the stuff that we're doing in class, you could probably abstract away to a library, right? But maybe you really don't like the way we handle shaders, right? Maybe you would rather put them in their own files. Maybe you want to, have them be reusable from project to project. You don't want to have to like copy and paste code, just put them in their own file. That's fine, you can do that. Typically they would have a .glsl extension and then you would just include that, for instance. Or you would include it as a string in an HTML document, which is kind of a very bizarre way to handle it. But I do want you to kind of take a, maybe a step outside of normality here And think about the fact that we are compiling code in a browser. If you have done HTML work and JavaScript work in the past, there is no compilation happening. It's just interpreted as you go, right? But the browser is actually going down and compiling our GLSL code. So just a slight difference. If you want to handle shaders in multiple ways, or sorry, in different ways, again, you can. One way is to use a null terminated string, meaning that if you're coming out of the C, C++ world, your strings need to be null terminated with that /0, if that sounds familiar. If not, basically you have to make sure that your string is formatted in an appropriate way. And that effectively means that you are passing in a single string with all of your shader code. This is not an ideal way to do that. Basically, you pass in a variable with a long string of your shader, like minified looking kind of a thing. Getting like a very bizarre duplication in my headset, but I'm not seeing anything on my settings, so I think my camera did something weird to my audio. You have seen the string thing before, yeah. It's not pretty. Interesting, okay. Yeah, it's kind of fun to see this stuff in the wild. So another way you can do it, store it in HTML, like put it in a div object or in some kind of an object, and then use getElementById. As a fallback, if asset loading fails, it can only, oh, okay, I could see that. Yeah, Philip's got a very good point. Have a fallback if things don't work, right? If you're missing assets or if something gets corrupted, have, you're missing texture like you see in Gmod or some of the TF2 maps or something like that. All right, so insert it in HTML. That's basically what we're doing, but you could basically put it into a div, for instance, call getElementById and pull that in, or we're storing it in the vertex shader script. We're pulling it in that way. That's kind of what we're doing. You can also store it as a file. So I mentioned you could store it as like a .glsl file. You can read that into an object, basically load a file in using the browser and using JavaScript. But if you go that route, you do need a web server behind the scenes, typically. So the one thing with that one, and I've got some code here in a moment for that, browsers do not like loading files, external files in. Like they don't mind images, but once you start including things that are not a JavaScript file or not an image or something like that, it really wants a web server to prevent security problems. And with a GLSL script, I mean, you kind of have direct memory access, right? So it kind of makes sense that there might be a security concern here. All right, first look at it though. So let's add a vertex shader. Okay, var vertex shader, define our JavaScript element, or sorry, ver, that should be var. For our vertex shader and then grab the element. So basically we have some object in HTML somewhere where we're going to get the element by ID. Again, we kind of do this already. But then here's all the stuff that we're not dealing with because we're using a library. So set the shader source, compile the shader, attach the shader, create the shader. I skipped over that one. This is all stuff that you don't want to have to do every single time. So make it into a library call, right? But what's the source? It's this vertex shader, which has been created, and the text of whatever this element is your actual shader code. Not very pretty, will work, but kind of annoying to use. Our method is pretty good. Here's the other way to do it, which again, this is a security concern because we're effectively performing a cross-site scripting request, which if you're not familiar with that, we're not going to really get into it, but basically somebody else is providing you with a file to load in, somebody else being some other user, and the browser can't just trust that. All right, there's a lot of well-known security problems with older browsers where that happens, and we want to really avoid that. But if we wanted to do it that way, you could make reusable code. You could abstract things out a lot nicer. Right? Just load in acid shader.glsl and make your, egg-based first-person shooter into a trippy, bended, like mind-bending type of environment. But could pull it in via Ajax. You could pull it in, however you want to load files in JavaScript. Have your nice, if you can't find it, then maybe have a nice fallback type of thing. But just another way to handle shader loading. Or there's our way, which is to use the simplified, easy way in our API where we have, right, our shaders as scripts. We give them an ID and we load them in, where's that at? Down here with the init shaders call. All this call is really doing is taking the IDs that you pass it and doing get element by ID and then pulling that information in and then doing all that stuff. Right? It's just abstracted out. But it kind of bears repeating that, again, this is a very particular library we're using here. The knowledge is transferable to other libraries, like there's Babylon.js, there's 3.js. They all do very similar things because they're WebGL libraries at their heart. Yep, there's other ways to do it, basically. Okay, summarize that. Load shaders in multiple ways. We're doing it the easy way. I talked about precision last time, but I'm going to show you a little bit of code for how to detect precision on your systems. Again, this has mainly to do with the fact that not every device that can use WebGL is going to have the same level of precision, right? Are you going to support phones? Are you going to support browsers only? Are you going to support ARM devices? What are you supporting for your application? Now, this is something that came from OpenGL ES, which is basically the embedded version of OpenGL, which is what WebGL is based on. And the key here is that it's possible that these systems don't support 32-bit numbers, right? They can support 64-bit, maybe 32-bit, maybe we're down to 8-bit. It just kind of depends on that system. Again, kind of less of an issue now, but maybe somebody's got a BlackBerry or an old Nokia that they want to use for your egg-based shooter. So, typically we need to actually specify this precision. There's not a default, so we actually have to say that. Every time we've done a program, you've seen precision medium P for float, right? But if you want to support high def, like you're making a beautiful HD 1080p application where the graphics fidelity is going to be incredible, you can actually specify, hey, maybe we're going to use a more cutting edge system which supports very, very high precision. So set it to high if that exists, or default to medium. Okay. And if you're looking at this and you're coming out of the C world, this should look very familiar. If you've never seen this before, these are compiler flags. Now, question for you, what does ifdef do? And I'm going to lean on those of you who have probably seen C before. So if that didn't come through, what is the purpose of pound ifdef? And if you said hashtag ifdef, you automatically fail. Boomer jokes. If defined, it happens during the compile process. Hey, this is a compiled language, right? So this is a compiler flag. It is basically an if statement where if it is true, yes, thank you, Phil, exactly. So what we're seeing here is that if these flags are true, then it will be precision high P. The compiler will never see this statement. If if this fails, it will never see high P and medium P will be included. Kind of the nice thing with compiler flags is this is an old C++ trick for basically having blocks of code that you can toggle on and off based on your system. It's like when I was in automotive industry, we'd use these flags all the time because all of our platforms would be using the same microcontrollers, but we might have like a camera, or we'd have a radar, or we'd have a LiDAR. The base code would be the same, so we just say pound if camera, do this. Elif radar, do this. So it's kind of nice for having all your code in one place and still, being a little bit cute with abstraction here. So you see if it is GLES, meaning it's embedded, And if we have the ability to have a high precision shader, use high precision. Makes sense, right? And then all of our floats will be in high precision. And this is going to be in your fragment shader. So if you want to support that, again, we're just going to be fine with medium P in this class at this point. Okay, so enough about shaders. Let's talk about Sierpinski. Even though you just handed in the assignment, let's talk about moving to 3D, because this is going to be more of what you're probably going to want to be doing in here, right? Let's not just do boring old 2D. Let's do 3D. So what is 3D to us? Well, he says, answering his own question, how do we make something 3D? We need an extra vertex, right? Or sorry, an extra axis. Extra vertex doesn't do anything for you, but you need that extra axis. You need that z-axis, right? If you have experience with 3D modeling, with any kind of like 3D CAD, Menger sponge time. That I'm not familiar with. Is that something that I need to know? Ah, it's a fractal curve. Okay. Three-dimensional. Okay. I have seen this. I didn't realize that's what that was called. Let me pop this over here. That's pretty cool. Yeah, I mean, if you want to do a Menger, looks German, so Menger. That's cool. I like that. Maybe we'll do that instead of Sierpinski. Anyway, you just need that third axis, right? So we need Z. For us, and for you all, it's really not that tricky, okay? So instead of vec2s, use vec3s, and you've been basically using vec3s anyway for vec3s and vec4s for colors. So for your vertex locations, it's just a 3D vector. If you're going to be setting uniform variables, right, we need that call to send, or basically to link that to our application, from our application to our shaders. We use gl.uniform2f. If it's in 3D, now it's uniform 3f. Pretty easy, honestly. It's not as big of a struggle as you might think it is. All of the algorithms that we're really going to be using for moving things around, you have to deal with that extra dimension, and it makes the matrix math a little bit trickier, but honestly, all the concepts are still the same. So it's not as hard as it might sound, the jump from 2D to 3D. But when you go to 3D, you do have the issue with rendering order. So we no longer just have like layers where I've got a triangle here, which one's on top? Oh, it's going to be this one. Hide the one on the bottom. Right, in 3D, we're going to have things going in 3 dimensions, so it's going to be a little bit more problematic. But fortunately for us, WebGL actually takes care of that, which is kind of nice. So we're going to have something called a GL depth test and a GL depth flag that we're going to set, where WebGL is basically going to keep track of what is drawn when, and it's going to layer it appropriately. So all of the occlusions that we're going to see are going to be automatically taken care of by WebGL, which is nice. It's one of the few times it does something nice for you. So don't draw hidden surfaces, right? We talked about that with clipping. Same notion here with hidden surfaces. Hopefully that makes sense. I'll give you some more examples here in a minute. But if we go back to the gaskets for a moment, and you're probably all sick of the gasket already, let's talk about this in terms of recursion. So you did the homework. Hopefully we understand what a bisector is, right? You just take the midpoint of these lines, remove the inner triangle, keep doing that recursively. You have a fractal. And here we have a nice fractal too. There's actually a great version of this zooming on David Hasselhoff's crotch, which he's clothed, but it's hilarious. Not sure who's going with that one, but yeah, there we go. Anyway, here's another fractal. This is a fractal too. What is a fractal? A fractal is a special type of object. It is not strictly two-dimensional, it is not strictly three-dimensional, which makes it kind of an interesting object to talk about. Fractal means fractional dimension. And all that means mathematically is that when you subdivide this thing out, right, when you start, say, performing recursion or running your loop, the area of this object goes towards 0. So the object appears to be getting, bigger, but more and more and more of it's getting cut out. Your area is actually going down. But the perimeter of all the shapes goes up. And this kind of odd behavior makes it a different type of object that we have to deal with here. So the filled area is the red, the perimeter is the length of the lines. You look at something like this, okay, makes sense. The area is going down, right? We keep removing more and more pieces, the less things are there. This example here is gasket 2, I believe, if I recall correctly. Gasket 2. Yeah, that's that one. One of the other things that you're going to see too is that if you look at gasket 2, I know you all did gasket 1 for your assignment. Where did you go? Are you open, I hope? Gasket 4? Nope, I must have closed it. All right. Gasket 2 should be a recursive algorithm, I believe. Yeah. So this is the algorithm I talked about like 2 lectures ago where it's actually recursive. And the reason we're kind of looking at this again, you might say, is that we're actually going to take this and turn it into a 3D object now, right? So we have a straightforward standard 2D Sierpinski gasket. One of the things to consider here too is that it starts choking when you increase the number of times it has to divide itself. So this needs to be my local gasket, not the web one because I'm modifying it. All right, so I said divide yourself 15 times, and it already chokes. So this is kind of one of the other things too where you're limited by some processing capabilities. Before we had, yeah, there, it crashes. Can't handle that much recursion. So n equals 5, n equals 15, it breaks, n equals 100, we're not going to handle that. If you start going down the recursive area, be very careful with your programming technique, basically. So I'm not going to, we already kind of talked about the gasket in depth. I'm not going to run through this again. If you are interested in the recursive definition, gasket 2 and beyond, use this divide triangle, and basically just it calls itself, calculates the bisector with this mix command. Oh, mix is something I did want to show you actually. So, and I had it in gasket 3, I think. And I've got too many different files open here. It's this one? Nope, it's in 3. So I wanted to actually show you what this mix command does. I'm not sure if anybody looked at it or not. Gasket 3, where are you? Did I really close you? Yeah. Just like me. Really? Is it gasket 4? It is gasket 4. Okay, I'm an idiot. You all knew that already. I wanted to kind of show you what this mix command does, just so that you can be aware. So gasket 4, please. Aw. Anyway, pop open a terminal here, or a console here. So this is gasket 4. This is our 3D Sierpinski gasket that we're going to talk about. It's kind of good to understand how to compute this bisector, mainly because it's doing that matrix math for you. And I'm just having you call it and not even worry about what it does, right? But it's kind of good to understand here that, let me go to the recursive function. Bop, bop, bop. Okay. So we are dividing this triangle up recursively. So finding that bicenter means finding the center point. And all we're doing with that center point is taking that vertex and pushing it onto our stack and then doing our removal algorithm with it, right? But for mix, I added a line of code here to just push some info to the console log. And this is helpful too if you're not great with JavaScript and if you're not necessarily, up and up on, web stuff. But this call to console.log is basically your printf. So it's your trace debugging statement. So what I've done here is I created two vectors. So two vec2s. So x is 0, y is 0, x is 1, y is 1. And then I said mix these two vectors at the midpoint. And if that makes sense, when I refresh this, here's my trace debugging statement. The midpoint is halfway through. Right? It makes sense. It did this calculation for me where exactly that vertex would be. So if we go ahead and zoom in on here, let's say this triangle or this tetrahedron here in the middle is our triangle. And it said, here is vertex 1, here is vertex 2. It found that bisector for me. Now mix takes in two vectors, and the parameter is where on that vector you want it to cut. And my question for perturbing the bisector is basically play with that point. Where is it? So if I did something like this, 0.75, I refresh here. Okay, it finds 0.75, 0.75 because we're between 0 and 1. But if I make my first vector negative 10.2 and negative 20.0, then my top right vector is 21 and 0. So it's not a simple statement. Okay, well, it finds the bisector at that particular percentage away. There's that vertex. It's just a simple little, vector-based formula that this function is doing for us. And I guess kind of the point was here is a function that's helpful to understand. Plus, here's how you can trace debug it right here in the console. And you can basically print any object that you want into that console. I could say console.log. Hello there. Because prequel memes are still fun. There we go. Again, trace debugging. The oldest tricks in the book are always the best, I think. And again, mix is basically just a nice little shorthand for interpolate. Hey, there we go. But again, this algorithm, it's recursive, so it's good to kind of understand how that works. It's a fractal. These techniques you could apply to other fractals. Like I'd be kind of curious to see if we could turn Sierpinski into something like this without killing your browser. I think I might actually try to figure this out later on. But anyway, that's the Gasket with a different perspective. What I want to get to before we're done today is talk about 3 dimensions because that's where we scale things up. We can still apply our basic Sierpinski algorithm to that. And if we want to take it to 3 dimensions, that's just another axis, right? That's that z-axis. So we need 3-dimensional points. And what is a 3-dimensional triangle but a tetrahedron? What is a tetrahedron? It is 3 triangles. And that's all this is. This is not a 3D object. It is a set of 3 triangles with common vertices to make it look like a 3D object, right? By putting this point here, we make it look like we're kind of looking at it from on high and it's kind of slightly cocked, right? If I want to rotate this thing around in space, I'm just moving these vertices around and these triangles are being redrawn to shape that, but it's still just a flat 2D object. Again, that's the trick with graphics is that everything's 2D. We're just being cute with where we're placing our vertices to make it appear to be 3D. So we need a list of 3-dimensional points here. And what do we need for this object? Well, 1, 2, 3, 4. 1, 2, 3, 4. And those are probably out of order. I'm not really doing it in any specific order. 4 vertices to define a 3D triangle. Send these to triangle or gl.drawArrays, gl.triangles, and you're good. So we have that. And how do we apply Sierpinski to this? Well, start with the tetrahedron. Go away, Google. Thank you. Subdivide the faces. So each of these is a face of this object, right? Same idea. Calculate the bisectors for each of these lines, cut it out. So let me pop ahead, and I've got a slide out of order here. Let's say you have a tetrahedron, pyramid, if you want to think of it that way. But calculate that bisector. So here is the midpoint of this line, midpoint, midpoint. You end up with removing this triangle, remove this triangle, remove the triangle on the other side and the other side. Obviously don't draw that. Pretty much identical to the 2D algorithm, which is kind of helpful. One of the important things to understand with WebGL, though, at least by default, is how that z-axis functions. X and Y makes sense, right? So if we go to paint here in our horribly drawn picture, there's our y-axis, here's our x-axis, right? Positive y is up, negative y is down, positive x is right, negative x is left. When we go to the z-axis, though, this here is negative z. This here is positive z. Okay? So just something to be aware of when you move to the 3D realm. Is that how 3D realms got their name? Probably. Anyway, positive z goes into your screen with our particular camera setup. So when you see something like this, this is our 3D Sierpinski gasket. So this is gasket 5 with only, I think, 1 or 2 subdivisions. Might just be 1 subdivision, actually. Yeah, because there's just these pieces cut out. You see the peak of the top triangle, right? So this would be on top. It's kind of like you're looking down. That first vertex is at -1 for z. So it means -1 is kind of closest to you. What do we see with this triangle, though? We see some occlusion happening, right? So this triangle, or sorry, this tetrahedron on top is covering up the ones on the bottom, right? This blue is not leaking through, it's being covered up. This green is not leaking through, this red's not leaking through. Based on the order on which this object is drawn, WebGL is going to hide the things that are underneath it. And even here, we see this part cut out. We're not like drawing any random stuff in here. There's no information to display. But just a couple of things to point out with 3D. Now, you might see something like this. Now, this is gasket, I believe this one's gasket 4. But I kind of want you to look at these 2 triangles. Or sorry, these 2 shapes here. So you might see something like this. And if you're looking at this and you're colorblind, I apologize. If you're looking at this and you're trying to figure out what the difference is, look at the green. So over here, you see the green's on top of the red, but it's behind the blue. Here, the green is behind the red and the blue. So this is what we want. Basically, we want these shapes to be drawn in the correct order. So we're defining how they're being put into the pipeline, and based on that order is where they are in our z-axis, right? Our z order, effectively. So here we've got a black triangle face here, a red one here, blue one here, green would be the underside, right? Here it's just all out of whack. And why is this happening? We didn't enable the depth test. What's the depth test, you might ask? Well, I'm glad you asked. So in OpenGL and WebGL, there's this thing called the Z-buffer algorithm. Basically, we are removing hidden surfaces. Oh, thanks for the question. I promise in class I'm not that self-deprecating in real life. Basically, it's going to hold your hand a little bit and only show you the things in front. So here with this gradient human and some different polygons, the things in front are what you see, the things behind you don't see unless you have like an opacity or something like that, right? But as you add objects to the pipeline, the order is being stored. And this is basically going to be governed by, okay, where are they at in the z-axis plane? So if they're closer to you, meaning that they're more negative, you see that first. If they're more positive, you don't see that. Keep in mind that's by default. So if you start playing around with the camera, right, I've got a nice IKEA coffee mug here, and I've got my camera in the standard location. If I start swinging that camera around, but the coffee cup stays in the same place, now whatever was here in front of it is going to hide the, here, let's use my water cup here. So there, I move things around, makes sense, right? Basically, WebGL is handling this for you, and if you're doing OpenGL, you'll have a very similar behavior, but it's known as the Z-buffer algorithm. Now, to use it in WebGL, you have to make two calls. So first, you have to enable the GL depth test. So you're saying to WebGL, handle the depth. But then, every time you render, you have to add in this depth buffer bit. So if you remember this gl.clear color buffer bit that resets your canvas to blank, or whatever color you set, you also have to OR in the depth. So it looks, excuse me, let's get rid of our debugging statement here. So depth. So here's the first one, enable hidden surface removal. This happens right after we define our clear color, after we define our viewport. Basically, it just has to happen in kind of our preamble. It's not in a specific order that it needs to happen. It just needs to happen before we render for the first time. So enable that. And at the very bottom in render, we have gl.clear. There's our color. There's our depth. Basically, we are telling WebGL, when you do your clear, here's the color. Don't forget about the depth, right? So this is gasket 4. Let me pop this back on the screen so that it makes sense. So here's buffer 4 is gasket 4. Subdivided 3 times. If I make it 1 time, this is what you saw in the slides. Basically just one face was cut out, or one tetrahedron was cut out. But if I get rid of this depth test, let me put it back to 3. So if we get rid of the depth test call, WebGL's pipeline isn't going to care. It's going to just go away. And we get something kind of nifty like this. All right, so I'm going to put that back in. What if we get rid of the buffer bit? So I'm going to comment that part out. It kind of depends. So if things start moving around, it may or may not keep an eye on it for you. Sometimes it will, sometimes it won't. But if I take out both of them, basically the first one is the one you really want to care about. And if we do gasket 3, I think this one of them was a little bit more apparent. I don't think it was gasket 2. No, gasket 2 is the one that's I've got set up incorrectly. Maybe it was gasket 3. Sometimes I like live coding just to show you all what can go wrong and what can't go wrong. For some reason, I was thinking disabling this didn't just make it black. I thought it messed up the... Okay, you need to not freeze on me. Gasket 3, please. Now, this is random, and it's not going to be helpful to see, because it's points. Perfect. All right. Anyway, enable the depth test, and add the depth buffer bit in too. You can't guarantee that the depth order will be preserved if this is not in there. I think we got lucky with the particular setup we had. If we muck about in chapter 3, there was gasket 5. Which is 2D. Never mind. For some reason I was thinking that was in 3D as well. But make sure we have that. Alrighty. So then this is actually going to be the last slide in shaders. Any questions on moving to the 3D location? Again, if it sounds scary to you because you've never messed with 3D, it's just another axis to keep track of. Algorithms are more or less going to be the same, and make sure that you enable depth tracking in WebGL. Otherwise, you're going to have a bad time. Our buffers basically look the same. Right, so we have our points array that we're flattening. Our vertex arrays are going to look pretty much identical. So let me move Gasket 2 side by side here just to kind of give you a 1-to-1 ratio here. So this is Gasket 2, Gasket 4 is what we want to show. Bop, bop. Okay, so scroll down. So var v position equals get attrib location, identical. gl.vertex attrib pointer, v position 3, v position 2. How many vertices are we dealing with here, 3 or 2? Everything else looks the same, right? gl.drawArrays, the same. gl.drawArrays, the same. There's really nothing too tricky here. The tricky thing with 3D is understanding how points can move around and rotate and stuff like that. The math just gets a little bit trickier in that regard. All right, questions on 3D at all? Or anything shader related? Because basically what we're going to start doing is building on our base knowledge of how shaders work and that kind of stuff. 3-D. In 3D. Put on your 3D glasses. Yes. Okay. Next thing that we're going to talk about is interaction and animation. I'll give you a short intro and then we'll be done. I'm not going to go deep into anything with 10, 15 minutes left, but we have a little bit of time, so let's talk about interaction. Animation I showed you before, right? So we have that rotating square in chapter 3. We've got this guy. Hey, look at that. It's not changing speed. I changed nothing on the code here, by the way. But we also have, let's see, square 3, because I think we have some extra information. Hey, let's make it go faster. What am I doing? I'm interacting. Yeah. I'm serious. Go and look at some of the older games that are out there that are CPU bound. And if you don't run it in an emulation environment or something like that, it's going to run at lightning speed. It's crazy. But yeah, bugs like this are awful. Anyway, animation, right? So things are changing. Well, that's why we don't talk to the business department. What do we see here? There are a few things going on that are kind of important to really consider. The obvious thing is this square is being animated, right? But let me get it to, can I get it to stop? Stop. All the way, please. That's going to be good enough. Based on everything we've talked about, what's going on? We have two triangles, or we have a triangle fan, depending on how it's defined, right? We don't care, effectively. The vertices are being updated every single loop iteration, right? And we can update those vertices wherever we want. We can do it in the application. We can do it in the vertex shader. It does, I was going to say it doesn't matter. It does matter because if you do it in the vertex shader, you're not CPU bound. You're using the GPU in that case, which is better. But point is, vertices are being updated. Fragments not being updated, but we could animate in colors and do all kinds of cool stuff too. Actually, that's this square EM, where I'm just clicking and dragging. Hey, colors, look at that. But rotating square, so we're animating. What do we need for animation? We need movement, and we need to clear out the old area. All right, so there's two things here. You're not seeing a trail, right? So this looks like a nice, clean albeit a little bit choppy because it's going really slow, right? If I made it faster, it'd be smoother. You're not seeing the background. What happens when we're drawing is that, okay, we can, that's kind of trippy when I follow it slowly. We have to clear the background every time. So every single loop iteration here, let me just pop open the code. Really? Okay, there we go. It's going to be tiny. I don't want to do that. Why am I doing that? Why are we doing that? Chapter 3, please. That way we can have nice big text. Rotating square 1. Rotating square 1. All right, so I showed you this last time too, I believe, where the vertex shader is the one actually updating the position. Again, we could be updating this theta in the application, sending it along. That would technically work too. Better to use vertex shader. But in our render function, we are calling gl.clear, right? If I got rid of this, let's see what happens. I'm going to have to open up the local copy. And this is where it's probably not going to do what I think it's going to do. Yep, it's not going to do what I think it's going to do. So why would it do that? Rotating square 1, right? So I would expect it to completely be a mess, like a mess. Are we actually doing this automatically for me? Probably are. If I do this. All right, something's going on here. That should be breaking it. Let's log theta and see if it's actually updating. Oh, it is. Okay, that's the right one. Well, why are you not doing what I think you're doing? It's got. I'm gonna have to look into this. So let me make a note to myself. Sorry, I don't mean to have all this dead air where nobody gets to the content they need. So what I should have done this demo before class. What I would expect to see is if I am not clearing the background, this should not be redrawn. I'm going to guess WebGL is holding my hand here and being nice to me. If I did this in any other engine, it would be a horrible mess of disgusting mess. But maybe Chrome's being nice, I'm not sure. Let's try this in Firefox. I kind of wonder. It's now I'm just kind of trying some things. What is going on? Save. Thank you. Firefox, where'd you go? No, you're not my default, sorry. You don't get upgraded that quickly. 367. Graphics. Chapter 3. Rotating square 1. No, you're not doing it. What about Edge? I think I've got Edge on here. Are you gonna play nice with my demo? Tell you what, Edge, if you play nice with my demo, you might get bumped up in the priority for me never to use you. Ah, okay, something's going on. Silly me. Typically when you clear the canvas, you clear it to that clear color and then you just redraw over it. You get something that looks kind of like this guy, right? So that's kind of what I expect to see. Ooh, look at all that WebGL error happening. But on the scale of a rotating square, so let me play around with that. Anyway, the key is that with animation, we have to redraw stuff, right? We have to give the illusion of motion. And typically what that means is that you are redrawing your background, and then you're drawing the shape with its new coordinates on top of that. So if I want to, say, take my coffee cup and render it and draw it, I'm going to draw it once. I'm going to move it at the end of my loop, or no, I'm probably going to move it and then draw it. And then at the start of the next loop, I'm going to clear the background, move it, draw it, clear the background, move it, draw it. And now it's off screen, so it's clipped off, right? But that's the illusion of motion. It's that frames per second with animation you hear about. How many frames are we showing? Basically, it's just your scene with things moving incrementally, and that's what movement actually is from this perspective. So we have that. And the other thing with this little demo here, and not this demo, I want this demo. The whole point is animation and interaction here. So I've got a couple of other things going on, right? I've got this nifty little slider. I've got a button. I've got my little menu here where it's not always clickable, but with the magic of JavaScript, these are clickable events. If you are coming from a standard graphics background, what I am doing is mind-blowing. And the reason that I say that is that I'm using HTML elements to define interaction, right? I'm using the browser. I have a button. Button has an on-click event. Button's got a little gradient. It's got text being drawn on it. I've got this little slider here, right? I've got my my drop-down list, my select menu here. I don't have to render any of this. The browser is. These are just HTML elements, right? So here you have a button. Here you have a select statement. Up here we have a slider. We can use these elements to our advantage and not have to code in the graphics for them. Right, one of the most annoying things with interaction and graphics is, okay, where the heck is the mouse? Calculate where the mouse coordinates are. Okay, am I over where the button is? Okay, I'm over the button. Does the screen resolution have any impact on how big the button looks? Things of that nature. Basically, just by using this, you're kind of shortcutting user interaction, which is great. And okay, maybe you want to look at something else. This little p-phi or this noise generator I made. I'm defining so these like sliders and stuff are baked into this language. I'm not defining these elements, right? And again, I'm really excited about this because having coded GUIs by hand in a graphical language is awful. Drawing text is awful in graphics. And being able to leverage the browser to handle that is utterly awesome. So what I'm going to leave you with here, before we get into interaction, and again, Tuesday we'll do an in-class lab over Zoom, use all of these things that you may or may not be aware of in the web world. Right here, I've got a little demo. I actually pushed this to GitHub. Actually, let me show you this because I also pushed that shaded triangle up. So if any of you want to play around with that, it is up on the, well, it's under chapter 1, but basically it's the lecture shaded triangle. Use jQuery. All right, so here is handling keyboard input, and I'm just typing on my keyboard. Here's all the key codes. So I'm pressing J, key chord 74, K, 75, number pad 1, 97. What does that mean to you? I could have a JavaScript function inside of, say, my WebGL application. If key code equals 97, do this. If key code equals 40, do this. Right? And all that really is a very, very simple listener where I'm waiting for a key press event. Right? So I'm waiting for somebody to press the keyboard. If I get a key, update this particular HTML element with that key code, but you can do whatever you want with that, right? If e.keycode equals, enter, move forward in your application or something of that nature. And again, this kind of stuff, the parallel in other wet languages would be that you have your forever loop for drawing. One of the things you do in that forever loop is handle user input. And in most of those, you have to like flush the event queue. You have to figure out, are they using the mouse? Are they using the keyboard? Are they doing a forever held down key press and use that library's keyboard handling calls? Here we can again just leverage the browser. And what we're going to get into is the preview for interaction and animation is that we're going to talk about some of these different devices. We're going to talk about how they can be used and things of that nature, different event types. But we're actually going to have to consider that in terms of a drawing surface. Right, so if we go back to this not the gasket, this square here. Here's my canvas, right? And if I click once, or if I click and hold, sorry, it's drawing squares where my mouse cursor is, right? I am not using the browser in this case. This is a WebGL application figuring out where my coordinates of my mouse are relative to this canvas, pushing vertices onto its list of vertices to draw, and then draw a square from that. So it's kind of, we got one minute here, so we'll end with this. It's not nearly as pretty, but effectively we have some calculations to figure out where the mouse is with respect to the canvas, and then start doing multiple levels of buffering, and it's a little bit more painful. So use HTML when you can with WebGL. Anyway, a little bit of a diversion there at the end. I've got some things to look up for you all, but any questions before I let you go for the day? Does everything make sense? Hopefully. Everything is good. Good. Good for now. Good to hear. Alrighty. Well, what we'll do again, Tuesday we'll do a Zoom meeting. I will probably release the next homework early. We'll have a little bit of an in-class exercise to get you up and running with some of this stuff, and should be fun. Alrighty, well, hey, ended right on the dot. Look at that. Bye, everybody. Have a wonderful weekend. I will see you all on Tuesday, and stay warm, I suppose. Have a good weekend. Stay safe. Bye-bye. Let's Northern Line sign off. Bye-bye. I gotta start off with, hey, everybody. Yes. Cringe-inducing, I'm sure. All right. See you, everybody. Bye.